4.1 is called Polynomial Functions and Models. So to start off, first of all, you do have a note sheet for this. If you want to use that, you can print that off. But polynomial functions, so you would have started to learn about these in Algebra 1, and one of the first things you learned about polynomials is just how to classify it by its number of terms, first off. So when you're classifying by terms, that's when you call it, if there's one term in the polynomial, it's called a monomial. So that would be like y equals x squared. And then you have binomial, trinomial, and then anything more than a trinomial, you just say a four-term polynomial, a five-term polynomial, etc. Then we also classify polynomials by their degree, and that would be like a first degree. What do we call a first degree polynomial? If the highest degree in the polynomial is 1, that's a line. So it would be, we have lines or linear, and then second degree is quadratic. And then cubic. And then there's actually quartic and quintic, which you might have learned about in Algebra 2 maybe, but you can also say fourth degree polynomial, fifth degree, sixth degree, seventh degree polynomial. A big idea is that polynomials, I think this was one of your questions on the bonus quiz, but the point is a polynomial is when you have a whole number power, as in not a fraction. Because when you have that fraction, that's when you'd have like a root, okay? Polynomials are smooth and continuous. That's going to be important as we get to calculus. We're going to use these two words a lot. You know, it's a good time to mention I've had a few parents, not a lot, but a few parents ask me or just mention their concerns about missing this last quarter and being prepared for calculus. And I promise you that it is going to be fine. You are lucky to have gotten through the most important concepts in pre-calc before quarantine. You know, you got to think about your younger peers or even siblings that are in like Algebra 1 and Algebra 2. Those guys learned some pretty important things in this last quarter, so they're the ones we should worry about and feel sorry for. Okay, so the fact is, if they're smooth and continuous, that means there's no domain restrictions. This isn't like a root or like a rational function. This one has no domain restrictions. And then another important thing about polynomials is that polynomials can be in standard form. Standard form is like your y equals a, this is the standard form of a quadratic, where it's in this descending order by degree. But then I want you to also recognize there's also factored form. And factored form is going to have its benefits for a lot of different things coming up in the next few weeks and the different things that we're going to be learning. Because factored form, you know, so if you have y equals x times x plus 2, okay, that would be factored form. If you were to distribute that out, then it would be in standard form. But factored form is nice because you can see the x-intercepts really easily in factored form. Okay, moving on from our little review. Real zeros. We've talked about before how a zero is a solution. It is an x-intercept. And basically, so all those things we talked about with quadratics apply no matter what type of polynomial it is, whether it's a cubic, a quartic, quintic, 6th degree, etc. So if you know that x equals, this is an example, if x equals -3 is a solution to a polynomial, then you know a bunch of things about what's happening at x equals -3. And usually in class, I love to try to get all 4 of these things just from you guys. Like, what else can you say if you know that x equals -3 is a solution to the polynomial? What does it mean to be a solution? So hopefully all of you are saying, well, I guess if it's a solution, that means it's a or an x-intercept. If it's a solution, -3 is, this is one of those examples where you do say and. I know I was maybe talking to a couple of you about how in math sometimes you use an in front of things because the first, even like x starts, if it sounds like it starts with an e, x-intercept. So you say an x-intercept. -3 is an x-intercept. Okay. A few other things. If -3 is an x-intercept, that means, so like over here, looking at this example over here, -2 is an x-intercept, right? So that means x plus 2 is a factor right here. Well, if -3 is a solution, that means x plus 3 is a factor to the polynomial. It's a factor to the polynomial. Those are maybe the 2 easiest things to pull out. The next one I'm going to write down is that something more about just writing about x equals -3. So writing it kind of in this form up here. X equals -3, if it's a solution to the polynomial, then it is a real zero, as in it's not imaginary. Oh my goodness. I have to write so slow and it's still, okay, it's a real zero. And then the last one, just something about if it is a solution, that means that it is an answer to when the polynomial is set equal to 0. So -3, it's really bad today, -3 is a solution it's a solution to f of x, the polynomial, being set equal to 0. Okay, so those are some facts we know if we know that -3 is a solution to a polynomial. Okay. Next slide. Find a polynomial in standard form of degree 3, which means it's going to be a cubic, whose zeros are -4, 1, and 2. Okay, so its x-intercepts are -4, 1, and 2. Well, if those are the x-intercepts, those are the solutions, then what that means is that x plus 4, x minus 1, and x minus 2 must be factors to this polynomial, right? This is just going backwards to what we're usually doing. Okay, so if these are the answers, then that means before we use the ZPP, we had these 3 polynomials these 3 factors in our polynomial. Okay, so if those are solutions, this implies that these are factors. So then to find a polynomial in standard form, I am going to have to do some FOILing and distributing, because this polynomial in factored form would look like this. And it doesn't actually matter the order that you write these, because multiplication is commutative. Okay, so we have this would be the polynomial in factored form, but it does say standard form. So guess what? We got to get some practice with distributing. So it doesn't matter which two you pick to FOIL first. I might just go ahead and FOIL these two. So this one is just going to stay here. And then we would have x squared. And then OI would be negative 2x and negative 1x, which would be negative 3x. And positive 2. Okay, so then now this isn't FOILing anymore. FOILing is only for two binomials. So now this is just distributing. So distribute this one to all three. So you should have 3 plus another 3 with the 4. So x cubed minus. Remember when you thought this was hard in Algebra 1? Like, oh my gosh, I have to multiply it that many times. Okay, and then final answer, I'm going to rewrite f of x so it looks nice in my final answer with combined like terms. So x cubed plus x squared minus 10x plus 8. Okay, so that is standard form, a polynomial with these three factors distributed. Now, I just went to do a hypothetical. What if this would have said degree 4, whose zeros are negative 4, 1, and 2? Now, if that would have been the case, what would you have done? Well, you would have picked one of these, wouldn't have mattered which one, and you would have squared it, okay? If you would have squared it, then it still gives you the same zeros. So like this one is x plus 4, gives you a 0 of x equals negative 4, but actually twice it's like it gives you that answer, right? That is actually the next thing we're going to talk about, which is called multiplicity, the number of times a factor appears. So in the last example, each of those factors only appeared once until I did that hypothetical, and I said, well, what if it had said it wanted degree 4? And I changed, what was it, x plus 4 to have a degree of 2. Okay, so state the multiplicities of the zeros for the polynomial, and then it doesn't list them. I need to write it out. It's y equals x to the 4th. Now that is technically x plus 0 to the 4th, so, or minus, it doesn't really matter which one it is, but that's the factor, okay? But we don't write that, okay? So then the next one, if you have your paper printed off, you already have this, but x minus 9 cubed times x plus 2.5 squared times x plus 1. Okay, so the multiplicities of the zeros. Well, let's just start with what are the zeros? Well, the zeros would be 0, 9, negative 2.5, and negative 1, right? So x equals 0, x equals 9, x equals negative 2.5, and x equals negative 1. That's from the zero product property. Now just stating the multiplicities, 0 has a multiplicity of 4 because it's raised to the fourth power. 9 has a multiplicity of 3. Okay, negative 2.5 has a multiplicity, this is pretty easy, right, of 2. And negative 1 has a multiplicity of 1. And these multiplicities, you're going to see in the next video, do have a very important role. They tell us something very important. So make sure you watch part 2 to find that out.